welcome. These are the slides for the chapter number 9 about copulas. So in this chapter, what basically need to take into account at all times is that we use this thing called copulas because the correlations might be misleading. You have this data series, so if you go to chapter 3, year 3.1, you're going to see this 4 scatter plots. So the scatter plots on X, you have these numbers, on the Y you have these numbers, and then you have different scatter plots. And then if you go and compute the correlation in the first scatter plot, you're going to find a value of 0.82. Then if you go and do the correlation in the second scatter plot, guess what? You're also going to find 0.82. And then if you do the same thing in the third scatter plot and the fourth scatter plot, in all of them, you're going to find 0.82. So clearly the correlations are misleading. So correlation is not really telling you what kind of relation there is between the X and the Y variable. So here I have plotted the distributions of the returns for the IPC and the VMAX. So here you see at the bottom on the X-axis the IPC. So the average is about 0, and these are daily returns. The minimum return is about minus 0.07, so 7%. The maximum return about 10%. And then on the y-axis I have VMAX, same thing, returns. So it goes from about minus 40% to about 60%. And then in the middle you see kind of the scatter plot of this, of the distribution of the two returns. So here you see a clear negative relation between the two return series. You see that there's negative returns, a very negative return in the IPC. So this data point here about minus 6%, which gives you about a 30% return on the VMAX. So here you would see, like, you clearly see the leverage effect. So when the stock market goes down, the IPC goes down, then the volatility goes up. We could represent the relation between these two variables with a correlation, but what we're going to do here is try to do this with copulas. One extra step that we're going to need is that we're going to see everything in the plane of the probability scale. Basically, this is exactly the same graph, but we have transformed the data from returns into probabilities. So here you see that tons of probabilities, again, like in the diagonal, showing that there's a negative relation between the two variables. And then at the end, what we want to do is, well, from here, if you have these probabilities, can we actually produce random numbers to be able to do something similar to Monte Carlo simulations, but now with copulas and not just with correlations as we saw in the previous chapter, in chapter 8. So a copulas overview. What are the threshold correlations? So threshold correlations is to compute the correlation between Z1 and Z2. So imagine Z1 and Z2 being two standardized returns. So you want to compute the correlation between the two of them, just as usual. But the only difference that we're going to have here is that we're going to choose Z1 such that it's smaller to Z1 evaluated, let's say, at a probability of 10%. And Z2 is also going to be lower than the Z2 with a probability of 10%. So the two of them are going to be kind of the lowest values that you find for Z1 and Z2. And then we're going to do this for all P's lower than or equal than 50%. And then we're going to do the other side for the P's greater than 50%. We're going to also compute the correlations. So how would this look in a graph? The very first square is one that goes up to 20%. So we would compute the correlations between the values. So here we have probabilities, but in reality it would be the returns that are in this square. So we go and compute, okay, what are the correlation of the returns in this square? Then we increase the square up to, let's say, 40%. And now we're going to compute again the same correlation, but only of the ones that are below 40%. And you see that it applies to X and to Y, and then up to 50%. And then we are going to do exactly the same thing on the other side. How does this look like? At a quantile of 15%, and then we compute the correlation between the two variables. So here we're doing the S&P 500 and the 10-year Treasury bond returns. So we see that there's a correlation of about minus 30%. And then we start increasing our quantile, and then we see that the correlation starts to go up, and it goes all the way up. So when we do only the left tail of both distributions, then the correlation is about 10%. And then if we do the right tail and we start at 50%, then it stays pretty much at a correlation of between 20 and 30%. So the rat tail has a correlation very stable, like positive. The left tail has a correlation, it's mainly negative. So clearly, if we go about using correlations, then, well, correlation only gives you one number for the whole series. So the correlation would be misleading because depending on where you stand, you're going to find different correlation between the two data series. And then in red, we have the threshold correlations that would be implied by bivariate normal distribution. So even the bivariate is not going to give you constant correlation, although this one is very constant, close to minus 10%. What is a multivariate standard normal? You have two variables, z1, z2, and certain correlation rho. And then this is going to give you the density function, the probability distribution for your two variables, z1, z2, given that correlation rho. Here you have the threshold correlation for different levels of rho. So for a rho of minus 30%, you're going to have this threshold correlation at the bottom. Then this would be for 0, 30%, 60%, and then 90%. The multivariate normal distribution, before it was the bivariate, now we're going to have multivariate. You can have n assets, so it's like having, okay, we have n returns and we have a correlation matrix across those n returns. So then how would the multivariate look like? Well, this would be the density function, and then in here we have how to compute the value at risk and how to compute the expected shortfall. Here everything is normal, so variables are normal, and then there's a correlation matrix in between. So this is not like adding two normal distributions and saying, oh yeah, it's also normal. No, in between you have this correlation matrix that tells you how the two variables are related. And then depending on this correlation matrix, you're going to have certain threshold correlations that are going to underlie the relation between two variables, two pairs of variables. However, here, as I said before, you can have as many assets as you want. You can also have a multivariate standardized t distribution. So you can think of this as something similar than the t distribution, where you're going to have kind of fatter tails. So here, fatter tails would be the relation between the two variables at the same time. What is there to say here? Well, you also have the correlation matrix. We can estimate the degrees of freedom using maximum likelihood, or we can just do it as we did before. Here, the only difference is, you see, well, we're using kurtoses, but as the summation of all the kurtoses of each individual security. The correlation matrix, either the regular one, or you can use the DCC approach. And these would be the threshold correlations that you get. So here, threshold correlations are linked not only to the correlation itself, but also to the degrees of freedom. So we have several combinations. So for example, here, the first row, 25% for these two, but 15 degrees of freedom. And you see that threshold correlation. So for the one that has 15 degrees of freedom, that's getting closer to normal. So it's very close to zero. Whereas the one that has 3 degrees of freedom, that's kind of very fat tails, it's going to give you a much stronger or a much higher correlation. This would be the threshold correlation for an asymmetric t multivariate distribution. So here you have again multivariate. So now you have two parameters, d and lambda, and then that's the lambda is the one that is going to give you the asymmetry in your distribution. So you see here that there is a difference between the left tail and the right tail of your distribution. So now let's talk about the Copula. So what the Copula modeling approach says is the following. There's this Sklar's theorem. So you're like, oh my goodness, now some theory. Well, this is important because it says that, look, let's say that you have many different variables with cumulative distribution function f1 for z1, f2 for z2, and fn for zn. Okay, so in this case we're saying kind of like each individual return distribution has its own distribution. So the return for IPC has its distribution, the return for VMAX, the return for interest rate. So imagine this as different returns for different securities. So what it says is, okay, if you have those marginal cumulative distribution functions, there exists a unique Copula function, and in this case we're going to call it G, that is going to link these marginals. But the word here that is critique is unique. So there's only one that can link those marginal distribution functions, right? And that thing is what we're going to call the Copula cumulative distribution function. So this G thing is going to be your Copula cumulative distribution function. And from this G, which is the cumulative distribution function, we can easily get the probability density function by just taking the derivative. And just as usual, if we have the copula, which in this case would be the G, so that would be the probability distribution function of the copula, then we have the log likelihood function of the copula itself, which should be the sum of the copula function plus the sum of the individual probability distribution functions for each zi. So this is in case we want to estimate the copula function and its parameters. So now let's take a simple example of the normal copula. The normal copula, we have the g function. So now in this case we're going to have the normal bivariate function with this row, and remember that here we're going to write row star. So in a second we're going to see where does the star come from. And then inside we have the inverse of u1, the inverse of the normal distribution. So this is the simple one, and u2. So now the row is the copula correlation between these two variables. This is not the regular correlation, but it's what we call the copula correlation. And that is going to be the parameter that we're going to estimate the normal copula. So here we have the PDF, and then with this log likelihood function, we can estimate the row star parameter. So this would be the bivariate case, and this would be the multivariate case. In here you have what would the threshold correlations look like for different levels of row star. So row star of minus 0.3% looks like this purple, then 0, and then one of 90% would look just like the one above. And then with copulas, we can also have a bivariate t copula. So in here you're going to have a t distribution, and you're going to have more parameters. So in this case you're going to have the row and the degrees of freedom, and you can also have the multivariate case. So this graph, I think it's the one that summarizes why we're using copulas. On top you have the normal copula. It looks very circles or something like that, but then the t copula starts giving more weights to the tails. So you start seeing how the tails get like a different shape. And then you can also have a skewed t, which is in the book, a skewed t copula that is going to have more weight here in the negative side for z1 and z2, or a skewed t copula that is going to have more weight on the right hand side. So that's the reason we would use copula, so basically to be able to model the tails of the distribution, but in this case of the joint distribution of two variables. Let's say you want to model two returns, and then you want to have tons of observations here to be able to compute the risk properly. So then in that case you're gonna need a skewed t copula that is able to tell you what happens in here. And as you can see, the normal t copula is not gonna be able to do that. That's the reason that in risk you would like to use copulas in general. How are you gonna use this in risk management? First, we need to build the copula model for returns. So you have some sigma from GARCH or something like that. You standardize your returns with that sigma, you get the zi. Next thing, you estimate your probabilities ui, giving certain function for each distribution. So in this case it's going to be like chapter 6. It can be normal, it can be a t distribution, and then after you have that, then you put on top of that the copula model and you estimate it. Then once you have estimated it, what do you do with it? Then do you do exactly the opposite? Now you're going to simulate probabilities u1 up to un from the copula model. You create those shocks, same thing that we did in the previous chapter, from the copula probabilities, and you're going to, once you create those shocks, you're going to create your zi's. Now these zi's, they're not going to be independent one of the other, because you have the copula on top. Then those zi's are going to have certain, let's call it correlation, but it's more than correlation. They're going to have like a copula type of relation. So it's something more complicated than just a simple correlation. And then from there, once you have the zi's, you multiply it by your sigma, and then you obtain your return. And then with those returns, you already know how to compute your var and your expected shortfall.